So this week we're going to pick up on limiter compressor. The limiter and compressor are kind of two names used to describe similar devices. There may be some difference in how people implement them. But the main thing is that what a compressor does is it takes signals that are in a certain power range and it passes them through unattenuated. This is the graphical transfer function for a power curve. And then if something has more power than a given threshold, it will attenuate the power. So what it does is it's a variable gain. It says, if your signal has a certain power, I'll leave the gain go through unaffected. And if it has a power above a certain threshold, I'm going to squash it or reduce the amplitude. And there are several benefits of it. You're effectively reducing the dynamic range. Now this gain over here can actually be much greater than 1. So it can be that not that it doesn't, that it just passes lower power signal and squashes upper power. It could be that it amplifies everything and squashes higher power. So that you've got a signal that has its dynamic range dramatically reduced, really, right? If you play a loud signal, it squashes it so that it stays clean, it doesn't distort, and then it gradually increases the gain so that the signal level at the output stays constant. The two fundamental parts are variable gain amplifier and the level detector. Now, it's not just a simple level, real time. If you're thinking analog, this is a power level detector, right? It needs to average for a certain period to determine the power over a short time window. Again, digitally, it's fairly easy to do. In fact, like I mentioned, it gets too easy when you have the whole vector and you can just process it and increase or decrease the gain. You can totally squash things if you really want to. With a analog compressor, you actually have an issue of the attack and release time. Since you can't post-process a vector, you're doing things in real time, you've got a certain lag, right? This level detector is going to have a certain time window that it operates over, and then it's going to affect the gain. So if you play something, if everything's quiet, this says very low level, gain's up high. When you play something loud, it's going to take a little time for that level detector to react. And that time it takes is called the attack time. It tells how quickly the level detector / gain adjustment responds to transients. Okay, now very often that is settable on a compressor. For instance, I think the one I brought in for demonstration has an attack knob. So you can set that. And what that does is it effectively takes a look at that time buffer, or time constant in the analog domain. So again, digital, you can be faster, but it still has that window. The alternative to that is, or excuse me, the other end, the complement, is the release, right? If attack is how quickly it responds to loud signals, release is how quickly it responds to, or how quickly it responds or goes back to normal for quiet signals. Okay, so I did a little example in MATLAB where I created this kind of square wave tremolo signal, and I put it through a 4-to-1 compressor. And you can see that, when it hits high, there's a little bit of time where the circuit reacts, or in this case, the MATLAB simulation reacts. So it's not instantaneous. And so this is the attack, the manifest of the attack time. And then over here is the release time, where you're squashing this loud signal, and then when it goes back to a soft signal, the gain's still really low, and it takes some time to come back. So this is grossly over-exaggerated, basically, so that you could hear it. Here, when it gets louder, it comes through a little bit more first, and that is often called pumping. pumping. You know, if you've got a compressor that's set for really high compression and if you play it, since you play something loud and then it goes away, it will amplify the noise floor at times, and it has this pumping sound when it goes back and forth on that. Okay. Examples. Usually you hear compression on clean guitar signals. You do get compression with distortion as part of distortion. You know, distorting does compress the dynamic range. But usually when we talk about compression, we mean clean compression. And trademarked, less dynamic range. It's got kind of a really extreme compression as kind of a subtle effect. It's not like flanging where it's really pronounced or something. But it is very noticeable. So one example I have is gas pipe you hear there's really not much dynamic. She's strumming the guitar, there's a lot of attacking going on there, but it's all kind of level. And it sounds a little unnatural. Okay. Whoa. Sorry. Okay. Another variation of a theme, if you will, here is what's called ducking. Okay, and this is, I've started to see this used for delays too, and it's kind of an interesting thing. The idea with ducking is that, okay, you've got a level detector, you've got a variable gain, and before they were both tied to the input. Well, there's nothing to say they have to be tied together. Let's use an auxiliary control thing on the level. Okay, so here we're going to affect the gain on this signal based on the input on this signal. And the most common example is, I don't have a musical example, but you'll hear it in the store, you'll hear it on the radio. If there's a record playing and the DJ talks over the record, now you still hear the record in the background playing very quietly while he's talking. That's ducking. Okay? They have it set up so that the DJ's microphone goes into the level detector and gets mixed into the output signal. And then the music goes through a variable gain amplifier, gets mixed in with the DJ's voice, but it has this level detector. Now, of course, it's probably all done digitally, but originally you have a ducking processor. Similarly, there is something called ducking delay, and what that does is it will vary the level of the delays you hear relative to the input. So if you're playing very loudly, there are less echoes, and when you stop playing, the echoes kind of come back up. So it kind of, if you've got a thick echo set, it muddies it while you're playing, and then it comes back up. Some of the newer digital don't do that. Okay, so we talked about compression. The opposite of compression, of course, is expansion. So if the compressor reduces the dynamic range, the expansion will bring it back. And in certain instances, these are used in pairs. You know, you may want to compress the dynamic range, you put the recording media, and then expand it again after you come off. If your recording media has a very limited dynamic range, you know, you compress it, you put it on the media, you expand it later. Similar, there is, we'll see an example of when we talk to acoustic compression next week. It's used in the telephone network. It's called companding in that case. And in that case, instead of doing a power-based thing, they actually compress the dynamic range on a level basis or a sample-by-sample basis. So you compress what's the equivalent of 13 bits linear into 8 bits companded. And that's used every day in telephony. But back to this expansion. The idea here is that if the gain is below a threshold, it's expanded. Right? So here, the curve is flopped from the compressor. Instead of having a unity gain or constant gain area and then a squash area on top, here it's an expanded area on the bottom and a squash thing on top. Or, excuse me, unity gain on top. Okay. One of the other things with an expander, kind of a limited case,